Hello, so this is our 36-2 lecture, our second lecture on relativity at the kind of conclusion, the extra bonus stuff at the end of 192. So last time I kind of brought up a couple different concepts. We talked about something a little bit strange at the very end, but the first thing that we covered was actually what we call Galilean transformations. There we are. Galilean transformations using inertial reference frames. This is typically just how we think about different perspectives. Right, we were looking at two different things, so imagine we've got two reference frames like this. You've got S and S prime. This is all a little bit confusing to look at at first, but you can imagine this. This is one person standing still, S, and this is one person walking forward, S prime. If something happens after some amount of time, and both people perceive that, the person walking sees it closer to them than the person standing still, right? Of course. But the Galilean transformations are essentially a set of equations that describe how we can go back and forth between these two perspectives. How can we all agree that that thing happened at the same place, even if relative to us, it happened in a different place? But these equations are basically saying, hey, here's how you can talk about it. If they're walking in the x direction, then we get something like this. X is equal to x prime plus v of t. And then we all agree on the same time. Right? If we all have stopwatches, if the person standing still has a stopwatch and the person walking has a stopwatch, and we both recorded at the exact same time the event happens, we should agree on the time. We can also do the exact same thing if the object that we're looking at has some sort of velocity as well. Right? If we take the derivative of this position equation right here, we can say, okay, well, then that is the speed as we see it in S is equal to the speed as we see it in S prime plus however fast S prime is moving, right? And that is to say, if let's say we've got our standing still person and our walking person, and there's a third person walking towards us. The person walking in S prime is going to see that person walking forward coming even faster, right? Those two velocities are going to be coming up together essentially, whereas the person standing still just sees them walking towards us at whatever pace they were. Right? It's those relative velocities. How do we all agree? Even if we would measure different things, how can we all agree on the same thing? Because physics shouldn't change just because we're looking at it from a different perspective. So there was a little bit of an issue with this though, right? And I brought up the fact that the Galilean transformations work very, very, very well, and they did for a very long time, until you start to go really, really fast. The Lorentz transformations are doing the exact same thing, but now we're assuming, or rather, we're not assuming that we can agree on the time as we could in the Galilean transformations. And that's largely because there is a speed limit to the universe. Everybody in the universe, regardless of how fast you're walking, right? If you're walking a third of the speed of light, you still are going to see photons traveling at 3 × 10⁸ meters per second. And the only way that can be true, that everybody agrees on the speed of the photon, is if different people experience time differently. So position will change relative to where you're at and how you're moving, right? Of course, that kind of carries over from Galileo, even if it changes just a little bit. But time now has a transformation to it. And what we're actually going to find here, if you actually try to plug in some of these numbers here, if you have anything less than an appreciable fraction of the speed of light. So what I'm saying is if you have some, say, single-digit % of the speed of light, then these relativistic effects will start to kind of pop up. Any slower than that, and it's really kind of splitting hairs about whether it's more accurate than the Galilean transformations or not. A lot of the time, what you would even find is that your calculator can't handle these numbers that are so small very well, because the number of decimals is just too many decimals for the calculator to keep track of. But we have this rule for the Lorentz transformations, and this is the more accurate, albeit a little bit more complicated version of the transformations that we know the universe actually follows. It depends on this gamma value, what we call the Lorentz factor, and the Lorentz factor is just some factor determined by how fast is S prime moving. So how fast are you walking? That's the velocity that you plug in for the Lorentz factor that shows up in these other things. So I keep talking about the fact that we can't necessarily agree on time, and how does that work? Well, in special relativity, we have what we call time dilation. Basically, the point of it is that if the photon is always moving at the exact same speed, if it's constantly moving at the exact same speed, that's going to be essentially our timekeeper. So there's this wonderful little description of how to think about relativity in terms of a light clock. I do recommend going through the reading for these things. If you're watching the lectures, it's worth it to just go through the readings real quick as well, because they talk about some really good thought experiments that try to describe some of these things. But more or less, what we have is that if you are moving, if you have a velocity relative to some other person that does not have a velocity, then you are going to experience time differently. And the way that we can measure that is, or we can compare our times by imagining something like the click of a stopwatch, right? Event 1 is turning it on, event 2 is turning it off. We have this thing called proper time. And proper time is just saying, hey, the stopwatch, the person holding the stopwatch has the proper time. The event has to happen in the same place spatially to get the proper time. So that is to say that if I was standing still and you were walking and we watch a rocket explode, and maybe it's a two-part explosion, right? Boom, boom. Neither of us would be able to record the proper time because neither of us are on the rocket. The rocket would record the proper time. If there's a stopwatch on the rocket, I don't know, some panicked crew member decides to take a relativity experiment real fast, and the first explosion, they click the stopwatch once. The second explosion, they click the stopwatch again. Their time is the proper time because they are the one that are standing still relative to themselves. They are in the frame of the rocket as it's exploding. Since we are both doing our own things not in the frame of the rocket, we will measure some other time other than the proper time. So the proper time we're going to specify is delta t of p. And you'll notice here that we're determining this based off of our t2 prime and t1 prime. And the reason for that is because looking at s prime, event 1 happens right here, event 2 happens right here, right? In both cases, the event happened in the same space relative to s prime, even though s sees them as happening here and here in different places. So with that proper time, we can then try to compare how does somebody standing in S compare, right? If I'm walking and I click my stopwatch, what's the person standing still going to record? And it's going to be just a little bit different. And again, so this is one of the kind of things that does not show up unless gamma starts to become some sort of real fraction where that is some percent of the speed of light. Any smaller than 1% of the speed of light, and you're probably not going to see these effects in any sort of real fashion, at least in your day-to-day life. Again, GPS is kind of a separate thing. But if we use the Lorentz transformations, if we say, okay, well, T1 must have happened at this time, and T2 must have happened at this time, then a lot of things actually end up canceling out. And what we're left with is that you can find how anybody else would record that time, delta T, as gamma times the proper time. So if our cartoon Einstein here is measuring, he is going to measure our delta t, whereas the person walking in S prime measures the proper time. And remember, since gamma is always strictly equal to or greater than 1, then any other time that we would see except the proper time, all times are going to be longer than the proper time. The proper time is essentially the shortest amount of time you could possibly record between two events, right? No waiting for the photons to travel or anything else. You're there in the moment recording with your stopwatch. So I want to try this on a whiteboard problem here. Say the diameter of the solar system is about 10 light hours, right? That's, roughly to get from one end to the other before we start getting down into empty space again. So let's say that a spaceship crosses the solar system in 15 hours as measured from Earth. So again, let's kind of assume that Earth is stationary for just a little bit, relative to this rocket at least, right? 10 light hours that's a pretty far distance. So let's assume that we haven't moved too much, especially because of how fast this rocket ship is traveling across the solar system. But do they experience the same thing? Are they going to also record 15 hours? That's kind of up to us to determine in this problem. We're going to use our time dilation idea here to think about what's actually going on. So, strictly speaking, we know that if the diameter is 10 light hours, the shortest possible time it could take would be 10 hours, right? If they were moving at the speed of light, it would take 10 hours to get across the solar system. You couldn't go any faster than that, right? Any faster than that, and the universe is broken and a bunch of nonsense. So, what we've got to do, though, is we've got to kind of look at this thing and figure out what's going on. So this 15 hours is actually telling us a lot about how we perceive them to be moving, right? So from the rocket ship's perspective, they're standing still. The universe is coming towards them, right? They're going through the universe from our perspective, but from their perspective, the universe is just coming towards them. They're standing still on the rocket ship. So this 15 hours is essentially how long it's taking from our perspective. What we can do with that is that we can say if the rocket ship, let's draw this thing out here. If the rocket ship is moving like that at some sort of velocity, as we're seeing it, this velocity v is actually our 10 light hours, and that should be an L. Light hour divided by the 15 hours it takes. So in the 15 hours that it takes, what we're basically saying, hey, this is moving at 2/3 the speed of light. Right? Because a light hour is just how far does light travel in an hour. It is the speed of light times hours. So if you divide the hours back out, then we get the speed of light. 2/3 of the speed of light is the velocity that we're seeing, so S prime is moving at 2/3 c. That's the velocity of S prime, whereas Earth is sitting in S. So now what we're going to need to say is, all right, we have delta t. We measured this as 15 hours, but that's not necessarily what they recorded on the ship. So what we're going to have to do here is we're going to have to say, okay, well, what did they record? They recorded delta t prime, which we know because they're the ones standing on the rocket ship with the stopwatch in hand. That's the proper time. The proper time, well, normally we would have seen this as delta t is equal to gamma times the proper time. So we're going to rearrange that real quick, and we're going to say, okay, well, then the proper time must be equal to what we recorded on Earth, delta t, divided by gamma. Doing this, plugging this in, now what we need to do, we do need to find gamma first, right? Before we can actually plug this in. So we'll plug in for gamma, being 1 minus v squared over c squared, which go ahead and leave the c in there. So when you take v squared, that really becomes 4/9 c squared. The c's cancel out. So I've got 1 minus 4/9. 1 minus 4/9 square root of that. So that should be square root of 5/9, which is a little bit of a strange one. But if we actually plug in for these numbers, we can find this should be 1.34. So even at 2/3 the speed of light, we're only getting a 1.34 kind of gamma out of here. Like, to really make the crazy effects from time dilation, like what you might have seen in Interstellar when they got really close to the black hole, you have to have much, much higher velocities, or in that case, a very, very, very strong gravitational field. So we've got gamma is equal to 1.34. We come back here, we take delta t divided by 1.34, and we get back at the end of the day that the proper time should be 11.18 hours. So this is kind of a neat thing, right? It's one of those things that's really kind of interesting, of the idea of if you want to do like interstellar travel of any sort, the people on the spaceship are going to strictly have a certain amount of time that they're going to have to age, but the people back on Earth, you might go through multiple generations while it's the same generation on the spaceship traveling through the universe. And that's purely because of time dilation. The people on the ship are going to be experiencing proper time, whereas the people on Earth watching them go by are going to experience time much faster, right? And I do all these things, these are all relative terms, and that's why it's so strange to try and talk about these things. But kind of in a strictly speaking sense, as the people on the spaceship are going by, if they're watching Earth the entire time through a telescope, they are constantly seeing the people on Earth age faster than them. Time passes faster on Earth than it does for the spaceship. So, let's go back to our slides here. We've got another one, kind of on a similar thing. So in July of 2015, NASA announced that the Kepler spacecraft had discovered an Earth-sized planet in an Earth-sized orbit around a sun-like star. Right, and this was kind of a neat thing at the time. We were kind of imagining, hey, this could be a feasible Earth alternative if we were imagining it like that, or maybe there's life on that planet. Maybe the conditions are correct for that or something else. This was a good candidate to explore a little bit further. The only problem is that it is 1,400 light years away. So if you could travel as fast as a photon, it would still take you 1,400 years to get to that planet. So that is certainly not a one-generation kind of trip there. But imagine here that we can get really, really close. Right? Let's imagine that we can get a starship that can travel at 0.9999 C. We've got some sort of crazy spacecraft that can do that. Let's assume there's no startup and no ending time, where we immediately get up to that speed and we can immediately slow down once we get to the planet. So the question is, if we leave... perhaps we have some sort of crystal ball and we can see what 2020 is going to be like, and we're getting out of here. Let's imagine that you leave on January 1st of 2020 and it is your 20th birthday. You make the round trip. You go there, you come back. What year is it now on Earth, and how old are you? It's a bit of a fun question, right? And this is kind of one of the problems when you're talking about space travel, is that a lot of these trips kind of have to be one way. Because even if they are two-way, assuming, first of all, that you're not going to age out of this thing, then part of the issue that you run into with this is that even if you are not going to age out of this thing, then the people you come back to are certainly not going to be the people you know, right? They're long gone at this point. So... what we've got, though, is piece by piece on this thing. We're going to take 1 year to explore this planet while we're here, right? We spend 1 year scanning the planet, then return. So what we know is that from Earth's perspective, as they're watching this mission, the trip time is going to be however long it took to get there, plus 1 year waiting, plus however long it takes to get back. And let's assume that the journey back and forth is exactly the same. So then what we can say is that from Earth's perspective, how do we actually find this delta t? This delta t would be the distance divided by the velocity that we can move. So if it's 1,400 light years, and again, that's kind of an L, not a 1, 1,400 light years divided by however fast we can move, 0.9999 C. So the light cancels out with a light here, and what we end up with is that this single trip, delta t, is going to be equal to 1,400.14 years. So just a little bit longer, right? It's almost moving at the speed of light. You're getting really, really, really close. Okay, so we've got this thing going on, right? Delta t is equal to this thing. Now we come back to here. We say, okay, well, the total trip time is going to be 2,801.28 years. This is from Earth's perspective. So from Earth's perspective, we arrive back at the year 4818. Current year. So, how do we find how long we have perceived it to be? Well, as we would see this thing, so that's the current year as we have imagined this thing. What about us? From our perspective, we've experienced delta t p. So what we need for that, we're going to kind of treat this in the exact same way. Delta t of p is going to be delta t divided by gamma. We need to find gamma first. Gamma, our Lorentz factor, v squared divided by c squared. So this is 0.9999c squared divided by c squared. So get rid of the c squareds. You've got your 0.9999 squared and then 1 minus that. What we should actually find here is the gamma. Now this is an actual large gamma value. 70.71 is our Lorentz factor for this problem. So we can take our delta t for each of these trips. We're essentially going to see delta TP plus the 1 year, because we agree, we spend 1 year there. And then the trip back is another delta TP, the proper time. When we sum all of these up together, what we actually find is that the trip for us takes 40.6 years. So in this case, this is actually one that we could do in 1 generation, right? That's not necessarily always true, because 1400 light years is still a pretty close distance, all things considered. But, that's how long it takes. So we would actually be 60.6 years old upon return. But this is the kind of trip that could actually be done by one person, assuming, this is the big if, assuming that we can get a spacecraft to travel that fast. Because as soon as you start to go a little bit slower than this gamma value plummets. And as that gamma value plummets, our proper time starts to go way up as well. So this trip is possible, assuming that we can get to 0.9999c in a timely manner as well. But if that is no longer possible, that might be a multi-generational kind of trip at that point. So, one other really strange part about this, and maybe one that is not immediately obvious in the exact same way, is length contraction. See, when time starts to behave strangely, the rate that we perceive things, so too does length. Because photons do take some amount of time to travel from something, even though we imagine that photons travel instantly. On Earth, that is, for the most part, true, right? The time it takes for a photon to travel is near negligible in most cases on Earth. But if we start to move fast enough, the speed of photons being the upper speed limit of the universe does start to have some sort of strange effect on what we're actually going to measure for length. Because the near end of something gets, the photons from that near end of something get to us faster than the things on the far side. So what we can actually see is that just kind of like with time, different observers are going to perceive the length of something differently. And we have, in the same way, a proper length, and the proper length is, again, where the person is on the object, in the frame of the object. So the person on, let's go back to our earlier description. Me, you're walking, the rocket ship is exploding twice. The rocket ship had some length before it exploded, right? I can measure the length, you can measure the length, but the person on the rocket ship is going to measure something different from both of us, and they, being on the rocket ship, have the proper length of the rocket ship. You have to be in the same frame as the object to get the proper measurement, right? You got to measure the plank yourself. That's what you get for the proper length. If the plank is flying through the air, then all bets off, right? You're going to get something else. And so what we can do with this one is the way that we can try and relate these two things together is we can do something a lot like what we just saw with time. we can say, okay, well, S prime, the place where we're actually measuring the proper length, is going to translate out to us what length we might see, the difference between the left end and the right end. And when we sum all these things up together, we get a lot of things canceling out. And what we find is that anybody not in the frame of the object actually sees the object as being shorter. So the person on the rocket as it's moving is going to measure the longest length. But if we're outside of the rocket watching that rocket, we imagine this thing actually kind of shrunk down a little bit. And that's kind of a cool effect as well. And I've got a whole lot of videos in the next lecture to really kind of try to illustrate these things and how weird some of it actually looks when you start moving at relativistic speeds. But let's do something like this. So our good friend Jill has a rocket that they claim is going at 100, or it's 100 meters long. If that rocket is 100 meters long, and she flies it past your house, but you're measuring this thing, and you've got some sort of laser precision measuring tool, and you measure that it's only 80 meters long. Our good friend Jill has not lied to us before, so we assume that this isn't a lie as well. But they were moving. So length contraction might have something to do with this. Let's wonder for a minute here, what speed would Jill have to be moving at? What fraction of the speed of light would Jill have to be moving at so that that rocket goes from 100 meters proper length down to 80 meters from our perspective? So what we're going to do is we're going to take our length contraction equation here. So here's our rocket ship, measures 100 meters long, and that, from Jill's perspective, is the proper length. Now, from our perspective, whoops, let's go ahead and snag this thing. Let's make a copy of it real quick. From our perspective, it's a little bit like that. It's kind of jumbled up. We only see it as 80 meters long, and I've probably overdone it a little bit with this contraction, but that's okay. So we perceive it as being 80 meters long, moving at some velocity. From our perspective, S, it's only 80 meters long. So the trick is to find V, right? What we can say is that our length is equal to the proper length divided by gamma. So gamma must be the proper length divided by L, which we know is 1 minus V squared over C squared over 1. We got to do a little bit of algebra here. This is going to become L squared over the proper length squared is equal to 1 minus V squared over C squared. We got a lot of different things going on. I'm going to leave this as V over C as well. That's probably going to make this whole thing just a little bit easier. So what this turns into is that V over C is equal now to 1 minus L squared over proper length squared square root of that. And when we plug all of these values in, what we actually find at the end of the day is that Jill must have been moving really, really fast, because this is 0.6, or that is to say that the velocity is 0.6, 60% of the speed of light. So that's the kind of speed that it takes to get something to contract. And, you know, I would say a 20% contraction, that's a pretty appreciable amount, right? That's noticeable at that point. But it takes a very, very, very fast speed to actually get there. And again, keep in mind that 0.6c is a ridiculously fast speed. It is not something that we have ever achieved with any of our own rocket ships or anything like that. Not even close. This is a crazy fast kind of thing. It's all sci-fi kind of speeds. So this is kind of more of there's a really cool book trying to describe some of these things. And people have made different videos describing these. If you look up any sort of videos on this one, you can see where like the speed limit is 10 kilometers per hour, the speed limit is 30 kilometers per hour. How does the universe look? And it gets really weird. It gets really weird really, really fast. But the entire book is written in such a way to try and give you an idea of what the universe would look like if we were to start moving at these relativistic speeds, right? If you bring the speed of light down to something that's much slower that we can kind of understand and appreciate in our day-to-day life, then you can start to imagine how these effects might be morphing your world. And it's not to say that this doesn't actually happen. Because again, I think I've talked about this in lectures previously. When you are on an airplane, you are technically aging slower than everybody else on the planet. Or from your perspective, you're not aging any different. They're all aging just a little bit faster. But the amount that they age faster is so incredibly small that it's not something that's really perceivable to us in any sort of real way, right? It's in an amount less than how far our clocks get off. So there's not any sort of real way for us to measure that in any real sense, but if you start to get up to these speeds, or if you have large gravitational fields or anything like that, then this stuff becomes a little bit more important. Or if you're working on very, very precise systems, right? Like atomic clocks or GPS or anything else like that that depends on very, very fine timekeeping, then these effects do matter a lot more. But it is a really cool story. There's a link to one of the books if you're interested in getting that book to read through it. It's a little bit old, but it still makes the point very, very, very well. And there's a lot of fun videos that have taken on this idea and, tried to make something out of it. So here's kind of a quick concept check more than a whiteboard problem. Let's imagine in some sort of dream, because you've been thinking about this relativity a lot recently, the speed of light is no longer 3 times 10 to the 8th, but all of the rules of special relativity are still valid. You're at some sort of track meet. You're in the 100-meter dash. You've got your own stopwatch because, I don't know, the timekeeper looks sketchy or something. You race it. The timekeeper says you won at a speed of 10 seconds. Your own watch, though, says it was 8 seconds. Who measures the proper length? Who measures the proper time? We can calculate the speed limit of the universe based on this, right? This is kind of a fun thing. We do have one thing that we can actually measure here. But then who do you say measures the correct time? So going piece by piece through this, who measures the proper length? The proper length is the length of the track. You are currently moving. The track is not. So the timekeeper is the person that's actually going to measure the proper length. You, being the one moving from your reference frame, you are going to measure the proper time. Now, before I address part C, who measures the correct time? Now, that one's a little bit strange because there's not a really correct answer here. Both of you are correct. Both of your stopwatches were working properly. But the laws of the universe mean that the stopwatch that you had in your hand isn't quite, it's not going to agree. And there's no way to make it agree unless you stand still the entire time, and then it's not a race. Correct in this sense is not really a concept that we can go with here. We just have to agree that both observers are going to see something different, and they're going to measure something different, and neither of them are really wrong in that measurement. But let's find the speed limit of this universe really fast. So what we can say is that from the perspective of the timekeeper, let's go from the perspective of S. So they are going to see you at a delta t of 10 seconds, travel a distance of 100 meters. So you are moving at a speed of 10 meters per second according to them. According to yourself, you're moving not at all, right? Because you look down and you're still there, right? The track is coming towards you. You're not going towards the track. But they see you moving 10 meters per second moving down the track. That means that when we're talking about these differences, we have this difference now between proper time and the time that they recorded. We can go back to that equation and we can say, okay, well, delta t is equal to gamma times delta t of p. That is to say, gamma must be equal, whoops, one more down, gamma must be equal to delta t divided by delta t of p. 10 seconds over 8 seconds. And we're going through a lot of the same steps that we just saw before. Right? We're looking actually this time to find what C is. But I'm going to solve out in the exact same way, because if I get there at the very end, I'll have everything that I could possibly need. So this is going to become something like V over C is equal to the square root of 1 minus delta t squared over delta t of p squared. Whoops. I screwed up delta t and delta tp. Delta Tp should be on top right here. So delta Tp squared over delta T. When we come up with something like that, we have 0.8 divided by 10. Square that, 1 minus that. Or not 0.8 divided by 10, 8 divided by 10. And we come out of that is V over C is equal to 0.6, right? So just in the exact same way again, what we can say is that C, whoops, I said C must be equal to V divided by 0.6. 16.7 meters per second. So kind of roughly speaking, that's around some of these sort of values. When it's an appreciable value, something that we can actually reasonably reach in our day-to-day lives. Here is some of the issues that we could start running into. Track meets would become a nightmare. So with all of this stuff together, we run into a little bit of an issue, and this is kind of a strange thing. Simultaneous events are no longer necessarily simultaneous. If you're standing still and you watch two firecrackers explode at the same time, somebody else that's moving might not agree with you. They might see one happening after the other. Or somebody else could see it happening in the reverse order. And it all depends on how you're moving relative to each other. So simultaneous events are quite strange, but here's kind of our proof. If we go through these equations, say S prime sees event 1 and event 2 happen at the same time. That is to say T1 prime and T2 prime are equal to each other. But if they happened in different places, X1 prime and X2 prime, then when we actually plug in to find T2 minus T1 to see if it's 0 in the perspective of S, we find it's a non-zero answer. If X2 prime and X1 prime were different locations, assuming that it's not two things happening on the exact same space and time, then the observer that's standing still doesn't agree with that. They say, no, one happened after the other. I just watched it happen. And the person moving said, no, I just watched those two things happen at the same time. And again, there's not a correct answer. Both perspectives are correct in that sense. The Lorentz transformations are how we can agree between different perspectives. So, and here's a really fun one, and this is actually a real experiment that we had done, when we were first looking at what's going on with relativity and different particles and things like that. So, our good friend muon, the large electron, they are oftentimes produced by high-energy cosmic rays. Right, so there's a high-energy light going through the universe. Muons get generated from whatever purpose, but they actually decay very, very fast. Right, so they don't have a very long lifetime at all. But as they're traveling to Earth, they travel at a speed of about 0.98 times the speed of light. But we have measured muons, right? We understand muons fairly well, I think. And we have an exact expression for the lifetime of muons, or the half-life of muons. So the half-life of muons, and if you haven't done exponential decay in a while, this is the equation that we're looking at. But the half-life of muons is 1.52 times 10 to the negative 6th seconds. So 1.52 microseconds is how long they survive. This expression right here basically says, hey, from the number you had when you started, multiply by this exponential, and this tells you how many particles you should have left. So let's say that we had 1,000 muons detected on top of a mountain at a height of 2,000 meters. Now, that's 2,000 meters tall. By the time we get down to the bottom, we don't expect many. And actually, when they were originally doing this experiment, they didn't expect to see any muons because, again, this is a very fast lifetime. And realistically, from upper atmosphere down to the mountaintop, that's a pretty far distance, even for something traveling at 98% of the speed of light. So we didn't expect to see many at all, just kind of a statistical small amount. But what we actually found is that even at sea level, we still find about 540 muons per second at sea level. So it's a pretty fair amount of muons that still get through, despite the fact that they've got this very short lifetime. So, without special relativity, take our old classic Galilean transformations. How many muons should be detected at sea level? And then, take special relativity. Imagine that this lifetime is not the lifetime that we should be measuring, but the lifetime from the perspective of the muon, or the proper time. With special relativity, how many muons do you expect to find now? So, let's go ahead and try this out without relativity first, right? This will really give us a perspective on what we're expecting to see. So, if we started with 1,000, let's go ahead and steal this picture. Oh, it did that stupid vector thing again. Oh well. We'll just draw this out ourselves. So if we start on the mountaintop, at a height up... Oh, sorry, my draw pad's a little bit slanted. So here's our detection box, right? And let's imagine it's like a really, really steep cliff, and it's 2,000 meters tall. Versus our detection box down here. So up here, we saw 1,000 muons per second. We're asked to find how many are we going to find down here without special relativity first. So let's do this in red because it's not quite the correct perspective. We have to imagine that all of these particles, these little muons, are traveling down at a speed of 0.98 c. So then we could say, okay, well, the time it should take them to do that, as we measure it, should be the height divided by that velocity. So the time that we're seeing should be something like 6.803 times 10 to the negative 6th seconds. That's how long it should take to get all the way down, right? So that's actually a few lifetimes. So it's not that we shouldn't see any because it's an exponential decay, but we should see very, very few of them. So with all of that, we go back to our expression for exponential decay. So this is the number that we see is n naught times an exponential of negative, and let's go back to this thing. This is negative natural log of 2 times t over the half-life time. Natural log of 2, which is just a number, times t over t half-life. Where again, the half-life is a known value. The half-life of the muon is 1.52 times 10 to the negative 6th. So based off of this, I'm expecting this thing to have halved in the number about 4 times or so, right? Maybe a little bit more than that. So I would expect it to go down to 500 for the first, 250, 125, and then something like 60 or so muons are what we expect to find once we're at sea level. And then I'm off by a little bit here. When we actually plug in these numbers, the 1,000 times this exponential, plugging in the time that we found, we get something like 44.95 muons, right? Which again, we're not going to see part of a muon. It's going to be averaged out over many seconds. We would find 44.95 muons. So yeah, that's roughly around the number, same order of magnitude, decayed a little bit more in that time, something like that. But I said before, and kind of in my notes here, that's not what we find. What we find is 540 muons. How does that compare? Well, what this actually turns out to be is that special relativity is kind of messing with us here. Special relativity is messing with us in such a way. So let's do Galileo versus special relativity. In the special relativity sense, the time that the muons are taking is no longer going to be quite the same thing, right? Because it's decaying from the muon's perspective. From our perspective, the muons are actually aging slower. Time is passing slower from them. So we shouldn't expect to use this exact same sort of half-life and have it work in the same way. What we really need to do here is we're going to first need to find that gamma value. So in this case, when we plug in these values, our 0.98 c for our velocity, what we end up finding here is that we've got a gamma value of 5.02. Right? So that's certainly large enough to make some wacky things happen. So then, we saw that from Earth's time perspective, delta t is equal to 6.803 times 10 to the negative sixth. But the proper time, the time that the muon experiences, is going to be equal to this time delta t divided by gamma. That is to say, to get from the top of the mountain down to sea level, from the muon's perspective, only takes 1.355 times 10 to the negative sixth, not even one full half-life. That's how much the muon ages to get from the top of the mountain down to sea level. So when you take that number into account, now if we plug in this thing, negative natural log of 2 times the proper time divided by the half-life, what we end up finding is 539.1, which is right on the money for that 540 muon kind of value. Much, much greater. So this is kind of a really cool thing, because otherwise it would be a lot harder to study muons because we simply wouldn't have as many. But because of the lengthened lifetime of these things, because they're moving at a different speed relative to us, we get a really fair number of these things, right? That's over 10 times more muons than we expected to see at first. So it's a really kind of cool effect here. And it's, kind of like a measurable proof that special relativity is messing around with the universe and doing all of these things, and that there is a proper time. And time can be experienced from different perspectives, right? Interstellar isn't just coming up with sci-fi nonsense for the heck of it. Proper time and time dilation is a real thing that happens in the universe. So that is all I have for today for 36-2. Next time around, I do have a number of different videos to look at that we're going to go through a few different things here and, kind of get a perspective on what a lot of these things will look like. So until then.